Right. So today we'll be discussing three practicals, right? One is based on a glass lab and the traveling microscope. Other two are based on prisms, right? Prisms and optical pins. So those are the three practicals we'll be discussing today. Okay, so this 16th practical, write down the topic, 16th practical, determination of, write down, topic, right? Determination of the refractive index, determination of the refractive index of glass using the traveling microscope, using the traveling microscope and a block of glass and a block of glass. Okay, so this is 16th practical in the syllabus, 16th practical, right? Determination of refractive index of glass using the traveling microscope and a block of glass, right? So for this practical, we need traveling microscope and a block of glass. Traveling microscope, we discussed that earlier. I'll just briefly explain what traveling microscope is, right? So here, in this practical, we are going to find refractive index of glass. So for that we need traveling microscope and a rectangular glass slab. So as I'm giving you this, you can take notes, right? You can take notes. Whatever on the board, you can take it down as well, right? So this is how the traveling microscope is. There's a base. Clearly listen, right? You have to understand the function of a traveling microscope, at least briefly here. So for the traveling microscope, it has a base like this. Base. This base should be horizontal. You can draw this with me. And there's two screws here to adjust the, so you can make this horizontal. To make sure that this is horizontal, there's a spirit level on this, right? Then there's this bar, metal bar. So on the metal bar, this is calibrated in millimeters. Then there's a vernier scale attached to that. Vernier scale, right? Attached to this. Actually, the vernier scale is attached to the microscope at the other side. This is a normal microscope, right? So through this bar, this vernier scale is attached to the microscope. Microscope is like this. So we look from here. We can change the orientation of this microscope, right? We can change that. There's a screw here. That screw is, let's say, screw 4. Then there's a screw here as well. To make horizontal adjustments, there's this is scale calibrated in millimeters, and there's a part here as well. That is the vernier scale. That part is vernier scale, right? That part is vernier scale. Quickly draw this one, and if you have drawn that, thumbs up. Right. Take this down, right? Take this down. This is the traveling microscope. Just a sketch of the traveling microscope. This is called horizontal scale, right? This is horizontal vernier scale. This is vertical vernier scale. So from these scales, you can read how much these are moved vertically and horizontally. You can move this bar, this microscope, horizontally and vertically. Then the distance you move, you can read it from these vernier scales, this one and this one, right? So there's a screw here as well, but this screw is not important for this practical. Using this screw, we can make horizontal movements of this whole thing, right? But this is not useful here. We only need this screw and this screw to make adjustments to this microscope. So what we do is we place the glass slab here. We place a glass slab here, and through the microscope we can look at the glass slab. We are keeping it vertically, microscope. You can look at the glass slab. Then we can do our experiment. Right. So if you need, there's a small screw here as well. When you rotate that screw, you can move this whole microscope together. And you can adjust that. Then by rotating this one, you can fine adjust. You can move the microscope. By rotating this one, you can do fine adjustments of the microscope. You can do fine adjustments of the microscope. Okay, everyone taken it down? Right? Right. So before using the before using this traveling microscope, you have to do adjustments to this microscope, right? First thing is you have to make this base horizontal. So there are spirit levels, right? You have seen spirit levels, right? Like this. There's an air bubble inside this one. So you have to get it to the center. So when it gets to the center, we can say this is horizontal, and here is spirit balance, this is vertical. Once you do that, you have to do adjustments to get, you have to adjust this microscope to do the experiment, right? Then below this, right, adjustments. Adjustments in order. Adjustments in order. First one, write down first adjustment. Leveling base of the microscope. Leveling the base of the microscope. Leveling the base of the microscope. So you can use these screws, right, to do that adjustment. So there is a spirit balance on this base. Here it is not mentioned. You have to make the air bubble into the center when you adjust that. You can draw that from a side. This is called spirit level, right? Spirit level. Then second adjustment, adjusting eyepiece, adjusting eyepiece. Okay, adjusting eyepiece. For the microscope, eyepiece is this one. This one is objective lens. This lens is called eyepiece. First, you have to adjust the eyepiece. So to adjust the eyepiece, there is a crosswire inside the microscope, right? So if you get the microscope like this, here you have the eyepiece, right? Here you have the eyepiece. Then the another part, it includes the objective lens. So this is objective lens. Then there's the cross wires, right? Here it is, we have cross wires. Those are just two wires, right? Just straight wires. So by you can change the length between these two. By changing the length, you can actually focus cross wires on the eyepiece. Cross wires on the eyepiece. So then what do you see? When you look from here, what you see is a sharp image of the cross wires. Through the microscope, you should see this, something like this, right? So you have seen in, like, when you look through a sniper, right? There's a crosswire you see through that telescope there. This also has the same thing. So these are crosswires. So when you see crosswires sharply, then we can say eyepiece is adjusted. Eyepiece is adjusted. Right. Just draw this, right? Then third one. Focus the object by rotating, let's say this one A, by rotating screw A. Once focused, a clear inverted image can be seen on cross wires. A clear inverted image can be seen on cross wires. Right? So then the next step is you just have to focus this microscope. You can do that by rotating this screw. When you rotate this, whole microscope moves up or down, right? So depending on the distance, so when you place the object here, you can change the distance to that object from the microscope and focus the microscope, right? Then what you see is a image on this, object on this microscope. Image of the object on the microscope, and it is inverted, right? Right. So now the adjustments are done, right? Then the first thing you have to do is, so this is the base of the traveling microscope, right? You can just take a piece of paper and put a mark there and place it on the base. Then you can focus the traveling microscope. I'm just drawing a part of that, right? Traveling microscope here. You can focus this you can put it like a cross mark here. You can focus the cross mark from the traveling microscope. Then the traveling microscope has this main scale and a vernier scale. So from the vernier scale, you can get the reading. Let's say R1. So this is the lowest point, right? Okay. Then using those screw at the side, by rotating that, you can lift this microscope, whole thing, right? But at the second case, you have to place the glass slab. You place the glass slab. So at the bottom there is still that mark is there, right? So what happens to that mark? It has an apparent displacement. Now the object is here. It has an apparent, let's say, now the image form of this object is here. So we call this distance apparent displacement. Apparent displacement. And this depth, we call that apparent depth. You can take this down. This is called apparent depth and this is called apparent displacement. It is upwards. And this is the real depth, right? Real depth. Now, you have to focus the microscope not to this object, but to this image, right? To this image, you have to focus that. So to focus that, it is clear. To focus that, it is clear that you have to lift the microscope, right? So using that screw A, you have to lift the microscope. So it is lifted, right? And again, you can take the reading there. So this is the main scale reading, then the vernier scale reading. Let's say that reading is R2. Okay? That reading is R2. So this microscope is focused to image. Right? Image here. Then you need to get the real depth. You need to get the real depth. To get the real depth, what you do is, you have the same glass slab. You have to sprinkle a little bit of lycopodium powder, right? Lycopodium powder onto the glass slab. Then you focus the microscope to the lycopodium powder. So to focus that, you have to further lift the microscope using that screw. Let's say you lift this to here. Then you take the reading here. So let's say that reading is R3. This reading is R3, right? Take it down. And this is called lycopodium powder, right? Lycopodium powder. Take it down. Right? Okay, now we have 3 readings, right? 3 readings. So from these readings you can find, so the goal here, in order to find the refractive index, you need to get real depth, which is the thickness of the glass slab. Apparent depth, those is stuff, right? So As I'm writing, take notes. Real depth is what? Real depth. This much is the real depth. Here it is focused to R1. Here it is focused to the top of the glass slab. So R3 minus R1 should be the real depth, right? If you don't understand, let me know. R3 minus R1 is the real depth or the thickness of the glass. Then we need apparent depth. So what is the apparent depth? This much is the apparent depth. Okay, so how do we find that? Here, at this case, microscope is focused to the image. Here it is focused to the top of the glass slab, right? So if you R3 minus R2, R3 is here to the top, R2 is to this here. So R3 minus R2 should be the apparent depth, right? Take it down. Apparent depth is R3 minus R2. Then you know that theory. Refractive index of glass relative to air, because it is at air and we are finding the refractive index of glass, right, is equal to what? Real depth divided by apparent depth. NAG is equal to real depth divided by apparent depth. So this becomes the refractive index of glass. Then you can, since you know these values, you can simply substitute them. So real depth is R3 minus R1. Apparent depth is R3 minus R2. Okay, take it down, and once you take it down, thumbs up. There's an issue with the Zoom, right? I'll just turn it off now, and I'll send you the link again, right? Then join. Just give me like 2 or 3 minutes, okay? There's an issue with the Zoom. I'll send you the link again, right? Then join again. There's an issue with the Zoom, right? Right. Okay, so in this method, you can find refractive index of glass, right? Using the traveling microscope. So this is a very accurate method because traveling microscope is a very accurate measuring instrument, right? So these lenses are very accurate. So from this method, you can find the refractive index of glass, right? Right. But the thing is, here we did only one calculation, right? We have done only one calculation. Just a one direct calculation, you found this. Not a graphical method. We didn't go for a graphical method. So in a case like this, there could be random errors. Random errors could be larger in this case. Somewhat, if you need to decrease the random errors, you can take 3 values for refractive index. Let's say you got N1, N2 and N3. These are 3 close values, and you can get the average, right? So how do we get 3 values here? You know that this is a glass slab, right? So the glass slab has, if you think about from here, so this is the glass slab, right? Right? If you place the glass slab to this side, like this, then you can get the measurements along this. So using this, when you look from above, you can take a 1 value for refractive index. Then what do? Then you can flip this glass cube and do the experiment to this side, right? Then again do the same things and find a value for refractive index. Then you flip this like this, right? Then again you do the same steps. Like that, there are 3 different sides in a glass slab, right? So along those 3 different sides, you can do the experiment 3 times and find a value for refractive index. Then those 3 values, you can divide that by 3 in order to find the average, of the refractive index. So that would decrease the random error somewhat, right? Okay. Now the practical is over. Then we'll move on to some discussion points, right? Write down the first point. These are discussion points, right? As I'm telling, as you are reading, you have to understand what I'm saying here, right? Okay, take it down. If the glass slab is rectangular, comma, using its 3 sides, with different thicknesses, find 3 values for refractive index of glass. So if those values are N1, N2 and N3, so the average is this one, right? You can take this down. So this is a more accurate value for refractive index. Below that, right, this decreases the random error. Right. Then another point, take it down. The same method can be used to find refractive index of a liquid. Right? Okay. So let's say you have a beaker here, right? As I'm drawing, you can take this down. You have a beaker, right? And at the bottom of the beaker, let's say you have a pin, optical pin, it could be optical pin. Then you need to focus. It is the same method, right? Focus the microscope and get the reading from the vernier scale. Let's say that reading is R1. Then you fill, let's say, the liquid up to somewhere here. So then what happens? This is the object, right? Then due to this liquid, image of the object gets an apparent displacement upwards. Somewhat like this, right? So after that, what you see through the traveling microscope is the image of the optical pin, not the object, right? It is already lifted up. So to focus this one, what you have to do, you have to lift this microscope. So to lift that, you can use that screw, a screw. Again, let's say you lifted it up to here, and once you lift it, you can get the reading. Let's say that reading is R2. So now you have focused it here, right, to the image. Then what do? Now you need to take the real depth. So to get that, you have to put lycopodium powder. You have to sprinkle lycopodium powder onto the liquid. The specialty about lycopodium powder is it does not dissolve in just water, right? It doesn't dissolve in water. So you can put lycopodium powder and it floats. So to focus on to lycopodium powder, you have to further lift this microscope and then get the reading. That is R3, right? Similarly, N is real depth divided by apparent depth. So what is the real depth? This much is the real depth. So real depth can be taken from R3 minus R1. So that is the real depth. Apparent depth, this much is the apparent depth. So that is R3 minus R2. R3 minus R2. So these values you know, then you can simplify the refractive index of liquid. Refractive index of liquid, right? We don't stop here. For the liquid, we can use a graphical method. We can use a graphical method because the thickness of the liquid or the real depth of the liquid, you can easily change. You can put more liquid onto this, right? And change this real depth. If you take 6 different real depths by pouring more liquid onto this, then you can draw a graph. Right, so let's see how to draw the graph. Just take this to the other side, R3 minus R2. So R3 minus R2, cross multiply, right? To take this to this side, put n to the other side. Then 1 over n, R3 minus R1. Right? So R3 minus R1, what is that? R3 minus R1 is the real depth. That is the variable we change, right? By pouring water, you can control this variable easily, right? So that variable is what we call that independent variable, x. This is the what we change first, right? So depending on that, apparent depth changes. This is the apparent depth. Or R3 minus R2, apparent depth. This is the real depth. By pouring water, you can change the real depth. That is R3 minus R1. Because we can change that first, right? Depending on this one, when you change real depth, apparent depth changes, right? So this apparent depth is dependent on this variable. So we call this one y. So we have a y equals mx graph. Then you can get a bunch of readings for this. You can draw a graph, y equals mx graph, and from the gradient, you can find 1 over n. So this is a more accurate method. But we could do this for the liquid, right? Because we cannot change the thickness of a glass, but we can change the depth of a liquid easily. For the glass, we cannot do this. That's why earlier we couldn't go for a graphical method, right? But in this case we can. Okay, take it down and thumbs up if you have taken it down. Right? Okay, so at the home, you can try this question, 2018 A-level question. This is homework, right? 2018 A-level question, that is a easy question once you do this, once we discuss this experiment. So this is the homework, right? Okay, so that is everything about how to find the refractive index using traveling microscope and a glass lab, right? Then another important practical, that is the 17th practical. Write down the topic, determination of, now listen carefully, right? This practical is somewhat complicated compared to this one. Write down determination of the angle of refraction, determination of the angle of refraction angle of deviation, right? Determination of the angle of deviation of a prism, angle of deviation of a prism by observing the variation of deviation, caused by a prism, okay. Okay, so here we are going to use optical pins as well, right? Around the prism we are placing optical pins. So these are another set of practicals, very important, right? Oftentimes they ask this in the exam. Okay. So here, this is what we are going to do. We are going to get a bunch of incident angles. Let's say simple I. So depending on those incident angles, we can get the angle of deviation, not the minimum deviation. Angle of deviation, you can find this. Then at the second part of the experiment, we are going to find the prism angle, right? Since we know the angle of deviations at each cases, then you can find the minimum angle of deviation, which is d min. So once you know d min, by substituting this in this equation, by substituting those values in this equation, you can find the refractive index of prism material. So this is what we are going to do in this experiment, right? So for a bunch of different values of I, you are going to find angle of deviation on the prism. Then you can find the prism angle. Then by substituting those here, you can find the refractive index. So that is what we are going to do in the experiment, right? Right. So in the lab, let's say this is a drawing board or something, or this could be the table, right? Surface of the table. Then you place a white paper then you clip that to the board. On this board, you place the prism like this. So basically, this is what we are doing. So from above, you are looking at the prism, right? Prism and the optical pins are around this. So basically, this is about the practical, right? Just take this down. Take this down. Right. So these are the stuff that you are going to draw on that white paper, right? So let's say this is the paper. So you get the paper, right? So the first step, you need to draw a line like this. Using a meter rule or something, you can draw this line. Let's say AB line. So what are we going to do here? We are going to we are going to actually draw bunch of incident angles. So to here you draw the, let's say this angle. Let's say this is 20 degrees. This is 20 degrees. Then here you draw 30 degrees. You draw the normal, then draw 45 degrees. You just keep drawing these, right? About for 6 incident angles, you do the same thing, right? But here I'll explain how to do it for just a one. But as you are doing the experiment, you have to do this 6 times for different incident angles, right? Okay, I'll just explain how to do it for a one. So first you draw the normal, right? Normal. Then let's say the incident angle is this much. Let's say that is simple I. Then what do? You have the prism, then you place the prism like this. One side on AB line, you place the prism. One side here. So to this side, this is the incident angle, right? Then what do? So this is the how you would see that. So you have the prism here, here. So on this line, you place 2 optical pins. Here you place 2 optical pins on this line. Then place the prism, right? So the optical pins are here. You look from this side, right? From this side. So what do you see? You see image of this, let's say P1 and P2. So you see 2 images from this side, like this. This is the image of P1, image of P2. That is what you see when you are doing the experiment, right? You place 2 pins here. So you are looking at these 2 pins, but you cannot see these pins, right? What you see is, when you look through this prism, images of these 2, like that, in 2 different places, right? Let's say this one P, this one Q, and this one R, right? Just draw these 2. First, just take this down. Thumbs up, right? Once you've taken it down. One is P1, another one P2. So these are images of P1, P2 from QR side. So here the goal is, you need to find, so you know that this is incident here, this ray incident here, is incident here, then emerges from this side. So what you have to find is the path of this emerging ray. So that is the goal here, right? Okay, listen carefully actually what happens here. So I'll just draw this again. Right? So you have placed, let's say P1 here. Let's say P1, then P2 here. Right? You know that from P1, light rays goes to everywhere, right? To all the directions, light waves spread from P1. But we only need light rays incident on the prism. So these light rays are incident on the prism like this. There are many light rays like this being incident on the prism from P1. Then from P2 as well, light rays are incident on the prism. Light rays goes to the other sides as well, but we only need light rays being incident on the prism only, right? Right. Then you look from this side, right? You look from this side. You know that there's a light ray that goes onto P2, P2 as well. But that light ray is obstructed by P2 pin. P2 pin, right? After that, that won't reach here. Then what happens? So if you think about this light ray, right? This light ray, from P2 as well, there's a light ray coming like this. But if you think about this light ray, image of P1 is covered by P2. Here what happens is it is incident like, it refracts like this and emerges like this. Then you can see that. So what do we need here? There are many light rays coming from this side, right? But you have to move your eye so the P1, you will not see the P1. You will see that these, let's say this is image of P1, this is image of P2. So as you are moving your eye, this P2 will cover, image of P2 will cover image of P1. So you will only see, at a certain point, you will only see one image, not two images. That is the case, then we can say these two are in a one line, right? So from this you can see that. So this one is blocked by P2. This is blocked by P2. Okay, take this down and thumbs up. If you don't understand something, let me know. Right. Then what do? Once you identify that line, then you place other optical pins, let's say P3 and P4. You place these two optical pins, right? Okay. So you keep moving the eye, till you see only one pin, only the one image of the, because other pin is covered by the P2, right? Then along that line you place 2 pins, right, like this. So what do you have once you taken those? Then once you place these P3 and P4 pins, everything is complete now, right? For a one incident angle, you have taken the necessary measurements. Then what do? You remove the prism. You remove the prism, right? Then what do you have? So you have this line. On the white paper, you have this AB line. You have already drawn this line as well. You have drawn that. Let's say P1, P2. You have drawn that, right? After that, what you have is positions of these 2 pins. You have 2 punches here, right? You remove the pins as well. You have 2 punches here, like that. Let's say like this. These are the positions of P3 and P4. P3 and P4. So the initially light ray is going to go along this path, right? It was going to go like this. But because of the prism, it has deviated. Here. So that that path is found, then you draw a line along these P3 and P4 as well. Then you can draw this line and this line, right? This is the incident ray. It was going to go like this. But finally, as it emerges, that ray emerges from the prism, it has deviated this much. So this is simple D. This is the angle of deviation. Angle of deviation. If you draw it here, you can extend this one. Then this is the angle of deviation. Simple D. Then the prism angle is here, right? Do you understand? So everything is happening at this vertex. At this vertex. So the prism angle is here. So this is the angle of deviation. So using a protractor, you can measure angle of deviation. You already know the angle of incident angle, you know angle. Then using a protractor, you can simply measure simple D. So that's what you do. So this is for a one incident angle, right? You have to do this for at least 6 incidence angles. From like 30, 40, 45, right? You have to repeat this same procedure. Okay, draw this one as well. Right. So this is just for a one incident angle, right? So you have to do this at least 6 times. Then those readings, you can record them on a table. Let's say you got like these readings 30, 40. Just take this down with me. 50, 55, 60 and 70. Let's say you take this and you have about 6 or 7 values, angles of deviations, right? Now what do we do? Using D and I, we can draw a graph between incident angle and angle of deviation. So angle of deviation is the Y, right? Incident angle is what we change. So this I is X, this D should be Y. So to the Y axis, we put angle of deviation, incident angle to this one. Then you have to mark these coordinates, XY coordinates on the graph. So you will get marks like this. I mean coordinates like this. 1, 2, 3, 4, something like this, right? Then using a flexible ruler, you need a flexible ruler to place here, right? You cannot use just a meter ruler. You need a flexible ruler to place on this. Then you can draw a smooth line like this. Not a line, I mean a smooth curve like this. So once you draw the curve, you can find the minimum angle of deviation. This is where the lowest point, right? Minimum angle, we call that D mean, or we call that D, capital D. So at the minimum angle, you know that for a prism, I1 and I2 is equal and R1 and R2 also equal. In theory, you have learned that, right? Right? Take down this one and draw the graph. So that is how we find the minimum angle. Okay, so this is how we find the D mean, right? D mean. Okay. Then write a subtopic, finding prism angle. Finding prism angle within brackets capital A. Finding prism angle within brackets capital A. So here in the diagram, you have to clearly see where the prism angle is, right? Remember the diagram? It was here, right? This angle is the prism angle. According to the side we took, right? Prism angle is at the Q vertex. So here we are going to find the prism angle. So to find the prism angle, you have to identify the Q side of the, Q vertex. Then what do? You place the prism like this. Q vertex is here. And these are P and R. So what you do is, you place the prism like this. Then you draw a line like this, right? Then place P1 and P2. P1 and P2. So what happens? Part of this ray refracts into the frame. And there's a partial reflection as well. From this side, there's a partial reflection, right? So that when that happens, this I and this I is same. By using the method I explained earlier, you place P3 and P4 pins, right? P3 and P4 pins. Again, then you have another line. You can use the same pins, but I'll say P5 and P6. Then that gets partially reflected from this side as well. Then you place P7 and P8, right? Then you can take the prism out. Then you can do necessary drawings. So the drawing we are going to do is, you have to extend this line here, extend this line. If the prism angle is capital A, it is here, right? In theory, you have learned that if it is A, this angle should be 2A, right? If the prism angle is A, this angle should be 2A, right? Okay, take this down. These are two parallel lines, right? These two are parallel lines. Just draw this one. Thumbs up once you draw that. So these surfaces should be polished, right, for this experiment, because these surfaces has to act like mirrors, right? You are using image of reflection, not refraction. Reflection. Earlier you use refraction, right? Like about 80% gets refracted, 20% gets reflected, right? About. So these surfaces should be polished, well polished. So you have different prisms when you are doing this experiment, but we are using the same prism. So you have to make sure that it is polished. Polished means you can use using a cloth, you can polish that, right? Both sides. Okay, take it down and thumbs up. So this surface, both surfaces, those are polished, right? Polished surfaces. Right? Okay, so now we found uh, minimum deviation angle. D mean you found, and the prism angle also you found that, right? So if you need to find the refractive index, you can simply substitute those values here. In this equation, prism angle you know, angle of minimum deviation you know. You can substitute those and find the refractive index. Okay, write down below, write down by substituting d by substituting capital D found at first part and capital A found at second part in the equation below, refractive index of prism material, refractive index of prism material can be found. Refractive index of prism material can be found. Refractive index of prism material can be found. Then write this equation. So I can simply substitute A and D values, right, in order to find a refractive index. You have to remember this equation, right? Sometimes they give just a 1 mark just for remembering this, right? If you remember this, just you can get a 1 mark. Right. Then the special points I have to discuss. First, just take this down. Point 1, write down. When fixing optical pins vertically, they should be placed when fixing optical pins vertically. They should be placed at a considerable gap. So a unique line can be can be gained. A unique line can be gained. Unique line can be gained to represent to represent the light ray. To represent the light ray. Okay. So now listen, right? You know that you place these optical pins. So when you are placing them, you are not going to place them like this, right? Very close. You are not going to place, you are not going to fix them like very close to each other. You have to make that make them apart as much as possible, right? So you will have a very unique line, right, which will represent that ray. So they ask this in the exam, right? Okay, then the second point, take down second point. If QR, if QR side, if QR side is marked, if QR side is marked at the first part of experiment, at the first part of experiment, comma, after finding the intersecting point, after finding the intersecting point of P3, P4, after finding intersecting point P3, P4, and QR, comma, by drawing a normal, angle of emergence, can be found, okay, to the same line, right? The same angle of deviation, is available for this emergent angle as well, full stop. So we can increase the number of coordinates when drawing the graph, right? So this is no, Q is here, right? So this is the prism. Then there's the incident angle like this, right? I. We have already measured the incident angle, but we didn't measure the angle of refraction, right? Because we didn't draw this QR. We only needed simple D, right? We only needed the angle of deviation. So we didn't draw this one earlier. But in this sentence, what they explain is, if you draw this QR line, if you draw this QR side, what can you do? So you know this that you know these two locations, then you can draw this line. Draw this line. If you have drawn QR as well, what can you do is you have this one, then draw a normal to here. Once you draw the normal, you can find this angle between emergence ray and the normal is I2, right? Then you can use in a protractor, you can find I2, right? Then by this method, you can increase the number of coordinates. It is more coordinates, more xy coordinates, the better you can draw the graph, right? Let's say it is something like for I, for an incident angle 30 degrees, let's say you got 43 of angle of deviation. For an incident angle of 30 here, you got angle of deviation 43. So in that case, so this is 30. In that case, let's say this I2 is like 58. So for 58 as well, you have the same angle of deviation, 43, right? Now you have an extra coordinate from one. So you do the experiment once for a one incident angle, you have two coordinates. Why is this? You remember that reversibility of light? So if you send the light from here, it goes like this. If you send the light from this side, then this angle becomes the incident angle. And that also, this light ray also would move along the same path. It doesn't matter which direction you send the light ray, right? It will have the same path. If they have the same path, they will have the same angle of deviation, right? So for I1 and I2, we'll have the same angle of deviation. So just by doing that, this experiment one time, you can take two coordinates, right? For 30, if it is 43, and if you measure this angle as 58, for an example, right? 58. For 58 as well, without measuring, you can just directly put 43. That is what we call reversibility of light. I'm not going to explain theory parts, right? Those are theories. So for the same angle, incident and emergent angles, we would have the same, not the same, I mean, two different incident angles, we can get the same deviation. So you can like double the number of coordinates. So if you have more coordinates, it's better for the graph, right? When you're drawing the graph, it is easier and better and more accurate. Okay, don't draw this one. You don't have to draw this. We have earlier drawn this. Just take this table only. Take the table only down. I think you understood that one, right? You have two incident angles for the same deviation. This is the reversibility of light, right? Right. Then the experiment 18. This is the last experiment today, right? This is critical angle method. This is very important practical as well, right? Determination of refractive index. Write down the topic. Write down the topic. Determination of practical 18. Determination of the refractive index of a material. Determination of refractive index of a material by critical angle method. by critical angle method. By critical angle method. Right? So for this experiment as well, we need a prism and optical pins, right? So that is the way to do this as well. So this is the theory, right? You know that sine C, the critical angle of sine value of critical angle is equal to what? N rare divided by N dense. Refractive index of rare medium, refractive index of dense medium, right? But in this experiment, what do we do? At the outside of the prism, it is air, right? And for the dense medium, we get a glass prism. So for sine C, for air, in refractive index is 1. Air in a vacuum, refractive index is just 1. For dense medium, it is glass, Ng, right? So the goal of this experiment is to get a value for this critical angle. You need to find the critical angle. So once you find the critical angle, you know the sine value of that, then you can find Ng. Ng means prism material, right? Take this down. So for this as well, we have similar procedure, right? You can take this down as well. So you have the paper and a prism on the table. You can take this down. Then you are looking from above. Place in optical pins. Right. Earlier I missed a point. Remember that when we are finding a prism angle, we go for this complicated method, right? When you are finding prism angle, we went for this complicated method. But easily we can measure the prism angle, right? Just place the prism on a white paper. Then you draw the margins. Using the protractor, you can easily find a prism angle. This is for the previous practical, right? Previous one, not for this one. I missed this part. You can easily measure this prism angle. But why do we go for this complicated method? What's the reason? You can easily draw this one and measure this angle using the protractor. In both cases, we use the protractor, right? To measure the angle. What's the reason? The reason is, here you are measuring capital A. But here you are measuring 2A. 2 times A. So you know that when the measurement is higher, percentage error decreases, right? Or the fractional error decreases. Remember? So that's the only reason there, right? That's the only reason we go for this complicated one when we are finding a prism angle. Because fractional error decreases. Fractional error means least count divided by measurement, right? If the measurement increases, fractional error decreases. So that's the only reason there, right? Okay, just know that fact as well. Fractional error decreases there. That's why we go for a complicated method to find twice the prism angle. Right, that's it, right? That's now. Now this is the equation we go for this experiment. Sine C is equal to 1 over n. So if we find the critical angle, then you can find refractive index of the prism material, right? Then this image is very important. Don't draw, just understand what I'm saying, right? So you have this prism. In the critical method, right, you place a optical pin in contact with a side of the prism. So why do we use an optical pin? Why do we use an optical pin? Optical pins, the height of optical pins are usually uh, larger than the thickness of the glass, thickness of the prism, right? Otherwise, if this is short, optical pin is like this, right? You won't be able to place at the edge of the prism. It will be like this. So if the optical pin is, its height is enough, you can place the optical pin. So this is the thickness of the prism. You can place the optical pin like this. So that's why you need an optical pin for this one, right? Okay. So in this practical, in order to prevent the refraction of light rays coming from this pin, you need to place the optical pin in contact with this side. So it won't get refracted, right? It won't get refracted when you place in contact. So that's the first point. So if it doesn't get refracted, the rays from P goes everywhere, right? But we only need rays incident on the prism. You can think about a ray like this. You can think about this ray. A ray which goes perpendicular to this side. That ray doesn't get refracted from this side as well, right? Because it is perpendicular. Then we can consider a ray like this. Ray goes to this side. Draw a normal to here. Then what direction would this move? Away from the normal. It would incident here and move away from the normal. And it goes like this. Then you can think about a ray like this. Draw a normal. Then that also goes away from the normal. You always have to draw a normal, right? Otherwise you don't know whether it is away or not. So if you keep drawing, you can draw lines like this, right? To all the directions, rays goes. There's a particular ray, when it hits here, then the ray goes along the surface. So when this happens, we call this incident angle as critical angle. So this is the critical angle, right? So for the experiment, we have to identify this ray, right? In order to find critical angle. So that's the point of this experiment. So this is the important part, right? Important ray. So if you slightly increase, if you think about another ray that has a slight increase of, so as the ray is incident from this side, this angle keeps getting bigger. So if you slightly increase the angle, what happens? It causes a total internal reflection. But we say, because slight increase, C and this angle to be the same, right? Because there's not that much of a difference. So then what happens? Draw the normal, and this ray trying to move to this side, then it moves away like this. Then you can observe this pin. You observe this pin. Right? There's another important part here, right? If you think about another ray, let's draw one more ray. You can think about this ray. So it has a bigger incident angle than the critical angle. Obviously, this is going to be totally internal reflected. It reflects like this, right? So when it reflects, this angle is smaller. So the refracted angle also is going to be smaller. So that would come like this. So all the other rays would hit here and comes from this side. So you will see that as well, right? Those rays as well. So you have to move your eye from this side to this side in order to identify this ray. So what happens is suddenly, so what do you see here? What you see is image of P. Image of P is what you see. You see suddenly image of P disappears. That point is where you place those optical pins. You place these optical pins. Looking at that instant when image of P disappears. You place these pins, right? So that is what you do in the experiment basically. Just draw this and use a different color to draw this, right? Right. Another thing I have to say is this acts as this side, right? Acts as a mirror as well, right? So you have an object here. In a mirror, what happens? At the same distance, it causes an image, right? So that image should be along this line. This image, right? Here as well, it should be the case. I mean, this ray has to come like this, right? From this image. So this causes an image here. Then if you think about this side, all the rays follow this image. All the rays should come from this image, right? So it will be like this. Right. Draw these two lines as well. Write down pin, optical pin should be in contact with XY. Put XYZ. Okay. XYZ. Optical pin should be in contact with XY. Optical pin should be in contact with XY. So refraction from XY side, is prevented. Refraction from XY side is prevented. Then another to the same line, right? We need optical pin, an optical pin, since it is taller than thickness of the prism, since it is taller than the thickness of the prism. Then another point, move the eye from eye means human eye, right? Move the eye from Z looking at XZ side, until the image of the pin, capital P, disappears. And place P1 and P2 in line with that. Right? So I just explained that, but when you are doing the experiment, you don't see none of those rays, right? You have to figure those out using what you know. This is all you know, that these are the rays that you would get there. You have the margin of the prism, right? So on the white paper, you remove optical pins and the prism. Then on the white paper, this is what you get. You get X, Y, Z. You can draw the margin, right? Then you get the drawing of this. Then you have a punch here, hole. This is the position of pin P. You have removed that, but you have the position of P. What else do you have? Another thing you have is positions of other two pins. This is all you have, right? Then other stuff you have to create in order to find these paths of light rays, right? The remaining parts are all just creations, right? Those are creations. Okay, these are creations, right? So what do we do first? We can draw image of this one. So if you think about this as a mirror, this side you can consider to be a mirror. And at the same distance, there is image of P. There's an image of P here. Then other creation is you can extend this line till it meets XZ side. Let's name it as capital L. Then what do you do? Then you have to draw this line. IL line. And at the intersecting point, we have capital M, right? So this is a one line, but this should be inclined, right? This is inclined. This is a one line here, coming from I to L. Optical pin P, optical pin 4, P4, P3, P4, or P1, P2, doesn't matter. So here you have capital M. This intersecting point, you can name it as capital M. Then what happens? Then you draw this PM line. So what do you have? PML. PML is equal to what? 2C, right? The critical angle, 2 times the critical angle. So once we know PML angle, you can just divide that by 2 and find the critical angle, right? So if you know the critical angle, you can calculate simple n. So simple n is equal to 1 over sine c, right? Then you can find refractive index like that. Got that? All we had is margins of the margin of the prism and the positions of these 3 optical pins. So using all those, you just do these creations. You do these drawings, right? They ask you to do these drawings, right? In the exam, they have asked. You can check those past paper questions. I'll send you the past paper questions to try those at home. They ask you to draw these lines, right? Okay. Take everything down. So from the blue line, all the blue lines are creations, right? Those are what we just drew. Those were not gained from the experiment, right? All we gained from the experiment is black color parts. These are just drawings, right? So to practice this, you have to do those past paper questions. I'll send those past paper questions on to the group. Clearly understand, you cannot draw PM line first, right? There's an order to draw these lines, understand? First, if you want, you can either draw PI or P1, P2 first and find capital L, right? You draw this line first and find this point I. Then you extend this line till you get to the intersection of XZ. Name it as capital L. Then you can draw IL line. So the intersecting point of IL line is PM. Then only, finally you can draw the PM. Understand? Then PML is going to be twice the critical angle. Then you can use half of that value to find the refractive index. Okay. Everyone done? Thumbs up, right? If you are done. Lasal, have you done that? Okay. Then we'll move on to the last part of this experiment. Write the topic, finding critical angle. The topic, finding critical angle for glass liquid. glass liquid interface. Finding critical angle for glass liquid interface. Right? Okay. Now you have the prism, right? Here we need for the previous one it was glass air. For this one we need a glass liquid layer. So how to create a liquid layer? You get a microscope slide, put some water here, and place the microscopic slide here like this. Then due to the surface tension of water, you will learn surface tension later, right? Due to surface tension of water, this water sticks between the glass and the prism. It doesn't pour away, right? It just sticks to that, right? So here you have a thin liquid layer. Thin liquid layer. You can draw this with me. Thin liquid layer. Then this is microscope slide. Microscope slide. Right? And X, Y, Z. X, Y, Z. Okay. Okay, drew that. There's a liquid layer here in between microscope slide and the prism. Right? Microscope slide and the prism. So here as well, we are going to follow the same method, the earlier method, right? So you place the pin, optical pin here, in contact with XY side, optical pin. Then that is going to create image. Let's say this is PN. N is this one, right? Interface of the glass interface. Understand? It is the edge of the glass, this N. Not the end of the liquid layer, right? End of the glass layer. There's PN. So this glass layer, end of the glass edge, acts as a mirror and creates an image of P at the same distance I. Right? Now just forget that there's a liquid layer. Just forget for a while that there's a liquid layer, right? Only the prism is here, right? Only the prism is here. So what happens? This acts as a mirror and it creates an image here, at the same distance. So that's what mirrors do. There's no, forget this one, right? Only the prism here now. Right. Now we found I. Then for the critical angle causes here. It's still, there's no microscope slide, right? Only the prism, right? For the prism, let's say for this incident, then there's going to be a critical angle for this incident. Let's say for this one. Then what do we do? Then the image is coming from here, right? Then this has to go along here and gets incident to this side and get away. So this is the ray diagram which I drew earlier, right? This is the earlier ray diagram. Then we know that this is the C, right? This angle is C, critical angle. We found that earlier, only for the prism. But now there's a liquid layer outside. So let's say what happens whether the critical angle increases or decreases if there's a liquid layer. Remember this equation, right? Sin C is equal to what? N rare divided by N dense. Right? For the dense medium does not change. Dense medium is the glass, right? It does not change in both cases. But in this case, initially, for the previous case, this was 1, right? It was air. Now there's a liquid. Liquid has a higher refractive index than 1. So this is higher. So if this is higher, now the critical angle should be a large value compared to the previous one. Understand? Right? When there's a liquid layer here, critical angle increases. So how do we draw that? So if it is a large value, critical angle will be gained somewhere here, right? Somewhere here. Just draw this line. Let's say that happens here. Now you can clearly see critical angle is gained at a point somewhere here. Beyond this point, when there's a liquid layer, let's say that angle is C dash. Then the normal and the ray comes out. You place P1 and P2 pins here, right? For these ones, you do the same experiment. You move the eye from here to here. Then you place, when the image disappears, image of P disappears, you place P1 and P2 optical pins along that line, right? You do the same stuff. But here what you have to understand is that when there's a liquid layer, critical angle got larger, right? Compared to the previous critical angle, right? Take everything down. Write this one as well. Right. Then write a point. Write down, since at both cases, total internal reflection occurs at xz position of capital I does not change. Position of capital I does not change. Understood? For the previous, when there is no liquid layer and when there is a liquid layer, we have the position of capital I to be the same place, right? Get it? But the image position changes, final image position changes. But this position of I does not change, right? In the exam, they ask questions from that. Then for this one, so sin C is equal to 1 over ng. We found this from the earlier one, right? Then sin C dash is equal to what? Instead of air, now we have the liquid. Let's say NL. So Ng is this one, right? So if you divide this by this, sin C dash divided by sin C, what do you get? Sin C dash is NL divided by Ng divided by 1 over Ng. Ng cancels off, you can find NL. NL is equal to sin C dash divided by sin C. So this is the refractive index of liquid. Take it down.